Calculus 2 series. Today we're going to be diving into one of the most powerful ideas in calculus, literally the power series.
Yay!
By the end of this video, we're going to be able to, 1, determine the radius and interval convergence of any power series, 2, represent various types of functions as power series,
That's right.
and 3, use the power series to evaluate indefinite integrals. So let's break this all down and then build it up from the ground up.
Power series is basically like an infinite polynomial. So we've all seen polynomials, so it's just usually something like this. But what if we kept on going forever?
So we are now introduced to what is called a power series, which can be represented as the summation from n equals 0 to infinity. We have our Cn, which is our coefficients, and then we have A, which is going to be the center of our series. And then we have our x, which can be considered as the distance away from the center. The entire function of x minus a can be represented as the stretch from the center of expansion. So why is this useful? When we have continuing polynomials that get bigger, logarithmic functions or trig functions, they start to get a little difficult. So we use power series as a way of understanding them so that we can integrate them and differentiate them and really understand, just using basic algebra.
The key idea of power series is that they don't work for all values of x. They converge, that is, giving meaningful values only a certain distance from the center, which we saw in the definition. That distance from the center is called the radius of convergence, and the zone that it covers is the interval of convergence. So as we will see in our examples, there is some number r for which the power series will converge. And this is going to happen at certain points. So if x minus a is less than r, then it will converge. And at the places where x minus a is greater than r, then that's where the power series will diverge. And r is called the radius of convergence for that series, this series here. So the series may or may not converge where x minus a equals r, and that's why we're going to be testing the endpoints. So now that we talked about what the radius of convergence is, a closely connected concept is the interval of convergence, which is all x's, including the endpoints in certain situations for which the specific power series converges. So this is our interval of convergence.
So we'll go over an example on how we determine the radius of convergence and interval of convergence using this example of power series. So looking at this, we know right here, this is our A of n, and we're going to apply the ratio test. Therefore, we have the limit as n approaches infinity over this is equal to the limit. When you do this, when you multiply a fraction, when you divide by a fraction, it's the same thing as multiplying by the reciprocal. That's just equal to the limit as n approaches infinity, x minus 2 times n over 3, 1 plus. And then, since this right here can be factored out, we could do this. X minus 2 times the limit. n approaches infinity over n, 3, n plus 1. And this is simply just equal to 1/3. Final answer we get is this. X minus 2 over 3. Now, we know that we have to do less than 1. So when we get x minus 2 over 3 is less than 1. It allows us to know that x minus 2 is less than 3. And this is our radius of convergence. Now, you have to get the point. We have 2, 2. And then this allows us to do 2 minus 3, 2 plus 3. That's equal to -1, comma. So now that we have these points, we have to check each point. So we have x equals -1, which is 1 -1 over n. This is an alternating harmonic, and we know this because when n is even, so we got like 2, 4, 6, we know that a negative times a negative is always going to be a positive. So when n is odd, let's do n equals 3. Now this be a negative times a negative, which is positive. But you have to multiply it again, a negative, which makes it negative. So this is why it's an alternating harmonic series, because as you go to like 1, 2, 3, 4, when you switch between even and odd, the value goes from negative to positive on those sheets. Now we also have to check x equals 5. So now we have to rewrite the summation. 5 minus 2 to the n over n 3n. That's just equal to 3n over times 3n. These cancel out. So when you get the final answer as the summation equals 1 to infinity of 1 over x. And we know, also, I forgot to note, this harmonic series, it converges at x equals negative. And here, this is a harmonic series. So those converges, or diverges actually, x equals 5. So now for the final answer, our radius of convergence is equal to 3, and our interval is close bracket -1 because it converges at -1, then parentheses or open bracket at 5 because it diverges.
So now we're going to learn how to represent functions as power series. A big reason why power series are very useful. So remember what a polynomial is. It's just this, and in the case of power series, this really continues on forever. And many functions can actually be written as polynomials. Things like sin x, things like ln of 1 plus x, we can actually represent these as polynomials. But why would we want to do that in the first place? Well, polynomials are actually really easy to work with, or at least much easier to work with than like trig functions, for example. We can integrate them, we can take derivatives, we can graph them easily, and this would really allow us to apply these to other situations like indefinite intervals. Okay, so a power series is a way to write a function as a big polynomial that never ends, right? We just learned that. And so the simplest one is actually called the geometric series, which is 1 over 1 minus x is 1 plus x squared plus x to the fourth, and so on. And we can actually use this as our parent function to then modify different functions and make them a power series. So for our function, it's going to be 1 over 2 plus x, and we want to represent that as a power series. Recall that the geometric series is a very simple power series, and we can get our function to look like that geometric series function to turn it into a power series. Some key things to note is that this geometric series has this 1 minus term and this x term. The x term can ultimately be plugged in here, and ultimately you can calculate your whole series that really just goes on to infinity, right? So let's get started on doing this. So immediately I see the numerator is already 1, so that's fine. So we have to work on the denominator. I want to get that 1 minus term, and I have a 2, so the only way I can really do that is by factoring out a 2. So let's start with that. Okay, that looks good. We can take out that 1/2, right? This is still the same thing. We just took out that 2 from the denominator. But I have 1 plus some x term. I want it to be 1 minus some x term. We don't want this. So what I'm going to do is I'm going to create what I call double negative. And so what do I mean by that? I'll just show you. Right, after we work this out, that's going to become 1 plus x squared. These are the same exact thing. All the things we wrote here are really the same exact thing. All we did is we manipulated our function to make it look like that geometric series where we have that 1 minus term and then some x term. And then obviously we took out that 1/2. So now all we need to do is really just plug it into what we already know. So we can use the same format. We're going to keep the 1/2 outside and then do our sigma n equals 0, infinity. And we're going to plug in that purple x term. So negative x over 2 to the n. And there you go. That is your power series representation. From here, we can go on and find the radius of convergence, interval of convergence, all those things. We can use the method that we learned previously, or we can take advantage of the fact that we know the geometric series very well and use these terms up here. So let's plug in for this. Okay, so we can solve further. This will just be absolute value of x over 2 is less than 1. And ultimately that turns into absolute value of x is less than 2. So we know our interval will be 2 and -2. -2 and 2, right? And we can test the endpoints if we want to. But also, again, for the geometric series, we know that it diverges at its endpoints. So we don't need to really test anything. So we can get our interval of convergence to be -2 to 2. Alright guys, so before moving on to learning more about power series and how to use them and why they're useful, I feel that it's important to really understand the math that we're working with, right? What does this even mean? Like power series, representing things as power series, interval of convergence, radius of convergence. So I think it's really helpful to see it graphically, and we can use Desmos to depict this. On your homework, you will notice that you're gonna work with the 1 over 1 plus x term, where you'll be asked to represent it as a power series, right? After you get your power series representation, like we did in the last problem, if you were to start plugging in values, so 0, 1, 2, 3, 4, 5, 6, and so on, you get a function out of that, right? You get a really big polynomial that goes on forever. And this polynomial very closely resembles this parent function, 1 over 1 plus x. So you're going to notice that you get 1 minus x plus x squared. So now we have a parabola, but we can keep going. Minus x to the third plus x to the fourth minus x to the fifth plus x to the sixth. And you can see that it really starts to take on that same shape. And that's what we mean by representing a function as a power series. We can make it a polynomial, which is really useful because they're really easy to work with, and they're going to allow us to take integrals that would otherwise be way harder to take. We can also depict this with the problem we just did previously, the 1 over 2 plus x. And this can show us what we mean by radius of convergence, right? The interval of convergence. So the function we had was 1 over 2 plus x. And the answer we got was this notation right here. That 1000 you can replace with an infinity. Just Desmos doesn't really like it for some reason. And you're going to see that as soon as I graph it, it replaces that area almost exactly. Like you wouldn't really be able to tell that there was another function underneath that. But for some reason, it stops at that 2. So after that 2, our power series representation is really no longer valid. And that's why knowing the radius of convergence, right, the interval of convergence, is very useful. Because it tells us the values that our power series representation is useful for, right? The ones that it actually can depict accurately. That's why we have our interval of convergence be -2 to 2. And that's why our radius is 2.
Now, since we learned how to represent functions as power series, we're going to do the next step, which is using the power series to actually evaluate indefinite integrals. The standard form of a geometric series is 1 over 1 minus r, and that can be represented as a power series, which is just r to the n, and this converges when r is less than 1. So let's say you were trying to find the indefinite integral of 1 over 1 plus x squared. Well, there's no simple antiderivative for this unless you obviously know like the rule or you've seen it in a textbook what the answer is, but the actual answer stems from the power series. So since we know it's 1 over 1 minus r, we could represent that as a geometric series by placing it as 1 over 1 minus negative x squared, which is just the same thing as 1 plus x squared, and voila, now we get a power series. And this is just negative x squared to the power of n. So now when we take the indefinite integral of this power series, which is just the same thing as the function that we had, we just get, let's say we plug in n equals 0, negative x squared to 0 is just 1, minus x squared plus x to the power 4 minus x to the 8th to infinity. And then once you get that series, then obviously you could just get the elementary antiderivatives of all of these terms, and that's going to give you back to a function that could be represented as a power series, and obviously this one would be represented as arctan.
Okay, welcome back to hopefully the last example that you have to watch, if you are watching, on how to use a power series to evaluate an indefinite integral. And this is on topic 11.9 on page 789 if you're actually interested in looking at the theorem and kind of doing some examples on your own, because there are some in the textbook. So the example that I came up with was the indefinite integral of x over 1 plus x squared dx. And at first, obviously, this doesn't seem like it has a very simple antiderivative which it doesn't, but the matter of fact is that we could actually represent this as a geometric series, which is pretty cool because of the fact that it simplifies our lives much easier and gives us a simple answer. So as we recall, 1 over 1 minus x could be represented as the, sorry, my pen is messing up, but as the power series of this to the power of n. And now we kind of learned in the previous lessons that 1 over 1 plus x squared, which is just the denominator of this integral, can actually be represented as 1 minus negative x squared. Just, I'm not doing anything illegal, it's just, I'm just kind of putting two negatives, so I could represent this as a power series, and when we represent it in the standard form, this becomes negative 1n and then x squared n. And now you're probably asking, well, where can we actually put the x, because that seems like a big problem. Well, just recount the fact that we could just multiply this whole expression now by x, and if you remember from your basic algebra course, this is just the same bases, so the exponents add. So this becomes simply negative 1n and then x 2n plus 1. Remember, this is just to the power of 1, so 2n plus 1. And now we could apply the theorem. So let me rewrite out the integral. So now you have the integral of this still very daunting looking power series, but it simplifies pretty easy when you see the theorem. So now if you look back at the theorem, right, the theorem says that if you have a power series, then you could pretty much represent it in this manner where you have Cn. So here Cn is going to be negative 1n, and then you have your actual you have the actual one with the radius of convergence, which is x minus a. So here x doesn't have one, but for the matter of fact, it's just 0. So when you integrate it, this becomes, you have the power series still, and remember that we have this, so this is just 0, so it would cancel out, and then we have n plus 1, so we would have x 2n plus 2 over, well, hopefully n plus 1, and here n is just 2n plus 1, so n plus 1 would just be 2n plus 2. Notice how this looks like oddly similar to like the antiderivatives that you would do for like regular like for like x to the power of 8, and then you just tag along the negative 1n, and then you include the constant of integration, and you always have to remember that this is for only values less than 1 because of the radius of convergence. So just in fashion, I'll circle my answer now, and yeah, that's about it. So all we did was we pretty much identified x over 1 plus x squared. We pretty much represented it as a geometric series, and then we used the theorem over here to express our answer, and that's pretty much it. So yeah, thank you for listening.